Rudewright Academy. Learn it, teach it, remember it. Today we're talking about replication and the small piece of arithmetic that makes it trustworthy, the quorum. By the end, you'll know how distributed stores keep several copies of your data, how those copies can quietly disagree, and how one line of counting keeps every read honest anyway. Every storage system eventually faces the same fact. The machine holding your data will die. A disk fails, a power supply pops, a rack drops off the network. And if that was the only copy, the story ends right there. So we replicate. The same record kept on 3 machines, and now the data survives any one of them. But watch the brand new problem those copies just bought us. The record holds the value 3 everywhere. Now a customer updates it to 7. The news reaches replica 1, and it reaches replica 2. But replica 3 was rebooting at that exact moment, and it never heard a thing. Nothing crashed. No error was returned. Then a read arrives, and it happens to ask replica 3. It answers 3. Yesterday's value served with total confidence. The system just lied, politely. So this is the puzzle of the whole lesson. When the copies disagree, which one is the truth? Before any machinery, borrow an idea from committees. A committee doesn't need every member in the room to make a binding decision. It needs a quorum. Enough people present that no decision can slip past unseen. Let's try it with 3 members. Suppose every update must be told to at least 2 of them, and every question must be asked of at least 2 of them. Now pick any groups you like. Tell these 2. Ask those 2. The group you told and the group you asked share a member. Try to dodge it, swap the groups around, and they still can't avoid each other. Someone is always in both rooms. That shared member was there when the news landed, so the committee's story stays straight. Keep this picture. It is the entire lesson. Now, the 2 classic ways to organize the copies. School 1. Leader-based replication. One replica is the boss, the leader. Every write goes through it, and the leader streams each change down to its followers. Watch an update travel. The client writes 7 and the leader has it immediately. A moment later, follower 1 catches up. But follower 2 is still behind, and that gap has a name, replication lag. Because look what it does to a read. A read served down here comes back with the old value. A perfectly healthy machine giving a quietly stale answer. And there's a second cost hiding in this picture. The leader is a single door for writes. The moment it dies, that door slams shut. Nobody can write at all until the system notices the death and elects a new leader. That pause is called failover. Detect the failure too slowly, and you are down for exactly that long. Promote the wrong follower, one that never caught up, and you can even lose rights you already confirmed. School 2 removes the boss entirely. Leaderless replication. Every replica is equal, and a write is sent to all of the copies at once by whichever node happens to coordinate that request. Watch one write fan out to all 3 replicas together. And notice what a dead replica does here. Nothing. The store keeps accepting writes because no single machine is special, so there is no funeral to hold. But a question the leader used to answer for us is now wide open. The write went out to everyone. How many confirmations before we call it done? And when we read, how many copies must we ask before we trust the answer? So let's try the 2 obvious answers and watch them both fail. First, the lazy one. Wait for just a single confirmation. Here comes the write. Replica 1 confirms and we tell the customer, done. Instantly. But 2 of the 3 copies never heard the news. So now watch the read. It asks replica 2 and gets the old value. Stale again. That's the polite lie from the opening, made policy. Fast and wrong. Fine, so try the paranoid answer instead. Wait for all 3 confirmations every time. Now every copy always has the news and any read is safe. But kill one replica, just one, and look. The write collects 2 confirmations, and then it waits. And waits. Every write in the system is now stuck behind one dead machine. Watch the stalled writes pile up. You bought 3 copies to survive failures, and instead you turned every failure into a full outage. Safe and fragile. Neither extreme works. One is too few, all is too many, and the right number lives somewhere in between. And here is the heart of the whole lesson. Call the number of copies n. When we write, we don't wait for everyone. We wait for a write quorum, some number of confirmations, and we'll call that count W. When we read, we ask a read quorum of replicas, and we'll call that R. Here, the write quorum is these 2. And the read quorum is these 2. Now count the 2 groups together. The write group has 2 members. Adding the read group makes 4. And 4 is greater than 3. 2 groups that big, drawn from the same 3 machines, cannot avoid each other. They must share at least one replica. There it is. And that shared replica was in the write group, so it has seen the newest write. That is the whole rule. Write plus read, strictly greater than the number of copies. You don't need everyone. You just need enough that the sets always touch. Now let's put the rule to work, because it's a dial, not a single setting. First, break it on purpose. Write to 1, read from 1. Count it. 1 plus 1 is 2, and 2 does not beat 3. And there's the disaster drawn. The write landed here, the read asked over there, and the 2 groups never touched. A stale answer with no warning. The arithmetic knew before it happened. Now turn the dial the other way. Write to all 3, read from just 1. 3 plus 1 is 4. 4 beats 3, so this is safe. Writes got slow and fragile, but every read is instantly fresh from any single copy. A fine trade for data you read constantly and write rarely. And the mirror image. Write to 1, read from all 3. Cheap writes, expensive reads, still safe. Then back to the balanced middle 2 and 2. And this setting hides one more gift. Kill a replica. The write quorum only needs 2 and 2 survivors are still standing, so writes keep succeeding. The same failure that froze the whole system a minute ago is now routine. Now let's run the whole round trip, once, end to end, because one piece is still missing. When 2 replicas answer differently, someone has to win. So every write is stamped with a version number that grows with each update. Here's our fleet on a timeline. The record holds 3 at version 1 on all 3 replicas. The client sends 7 stamped version 2 to all 3 copies at once. Replica 1 confirms. Replica 2 confirms. That's 2 confirmations. The write quorum is met, and the client is told, success. Replica 3 was slow. It still holds 3 at version 1, and that's fine because we never promised to wait for it. Now the read. It asks 2 replicas, replica 2 and replica 3. Replica 2 answers 7 at version 2. Replica 3 answers 3 at version 1. 2 answers, and they disagree. So here's a question for you. Which value should the client trust, and why is it allowed to be sure? Pause for a second and decide. Okay, look at the versions. Version 2 is higher, so 7 wins and the client takes it. And notice why this worked. The overlap guaranteed that at least one of the 2 answers carried the newest write. The version number let the client recognize it. The stale copy wasn't outvoted by luck. It was outvoted by arithmetic. A quorum system tolerates a stale copy. What it must not do is let stale copies pile up forever. 2 small mechanisms keep the fleet converging, and the read we just watched almost performed the first one by accident. Look at what that read learned. Replica 3 answered version 1 while version 2 exists, so replica 3 just exposed itself as behind. And the reader is already holding the freshest value, so it simply writes 7 back to replica 3 right then and there. Watch it land. The laggard catches up, and the fleet agrees again. That's red repair. Every read doubles as a small act of maintenance. And there's a lovely side effect. The hotter the data, the more often it's read, so the data you care about most is exactly the data that heals fastest. The second mechanism works from the right side. A little later, a new write arrives. 9 at version 3. But this time replica 3 isn't just slow. It's down. Properly dead. The other 2 replicas confirm the quorum is met and the write succeeds anyway. But think about the update replica 3 just missed. It shouldn't simply evaporate. So a healthy node writes itself a hint. A little note that says, "This belongs to replica 3, deliver it when it comes back." And the note just sits there patiently. Then replica 3 returns. The hint is handed off, the missed write is delivered, and the replica catches up on everything it slept through. That's hinted handoff. So now you have the pair. Writes are patient, they leave notes. Reads are opportunistic, they fix what they happen to see. And between the two, the copies converge. And everything the read side just did compresses into a handful of lines you can write from memory in an interview. Let's build it, then run it. Ask every replica for the key, but wait only until enough answers arrive, a read quorum of 2. Then pick the best answer, the one with the highest version. That single line is the arbitration we just watched. Then the repair loop. Any answer that lost carries an older version, so its replica just exposed itself as stale and we push the winner back to it. And finally, return the winner. Now watch it run against the fleet. The read goes out to everyone. Replica 2 answers 7 at version 2. Replica 3 answers 3 at version 1. That's 2 answers, so we stop waiting. The best line compares versions and picks 7. The repair loop sees replica 3's stale answer and sends 7 back to it. And the function returns 7 to the caller. Quorum, read, version arbitration, and self-healing in a handful of lines. So which school wins? Let's race them through the same bad afternoon. On the left, a leader with 2 followers. On the right, a leaderless trio with a write quorum of 2. Both systems are humming, writes landing on both sides. Now, at the same instant, each side loses a machine. The leader dies. And one replica dies. Watch the left side. Writes are refused. The single door is shut, and it stays shut while the failover clock runs. Detection, election, promotion, every one of those seconds is downtime you have to engineer away. Now the right side. The right simply collects its 2 confirmations from the survivors and succeeds. No pause, no election, no drama. The failure was absorbed by the arithmetic. And that's the honest trade between the schools. A leader gives you one place that orders every write. Leaderless gives you a fleet where a machine can die and nothing special happens at all. Now, initial details that decide whether the arithmetic actually protects you in production. First, the inequality is strict. With 4 copies, writing to 2 and reading from 2 sums to exactly 4. And exactly 4 is not enough because a 4-copy fleet splits into 2 clean pairs that never touch. Greater than, not equal. Second, sloppy quorums. Under a partition, some stores accept writes on stand-in nodes outside the record's home set just to stay writable. Resilient, but now a read on the home set can miss a write that was acknowledged elsewhere. The overlap is only guaranteed when both sets are drawn from the same members. Know which behavior your store gives you. Third, never let wall clocks pick winners. If concurrent writes are resolved by last write wins on machine timestamps, then one server with a fast clock silently throws away another server's acknowledged write. Version counters are the honest currency. And fourth, the tail tax. A quorum operation finishes when the slowest member of the quorum answers, so every extra confirmation you demand invites one more straggler into your worst case. Freshness is always bought with latency. Quorums are a dial between staleness and speed, and pretending otherwise is how dashboards turn red. Everything in this lesson arranges itself on one ladder, from cheap to strict. The bottom rung, eventual consistency. Write to one, read from one, and let the copies gossip their way to agreement in the background. It's the fastest and the most available, and a read can be stale for a while. Fine, when staleness is harmless. The middle rung, the quorum. Write plus read beating the total, with versions to rank the answers. A read that follows a completed write is guaranteed to see it, through the overlap. You pay a latency tax for the extra confirmations, and you inherit the 4 gotchas we just walked. The top rung, strong consistency. The system behaves as if there were exactly one copy. Every read sees the latest write. Always, no exceptions. That takes a leader or a consensus round on every operation. It's the most expensive rung and the first to degrade when the network misbehaves. And watch the 2 arrows. Climbing the ladder, stallness falls, and cost rises. The skill is not living on one rung. It's choosing the rung per piece of data. So let's choose rungs for real data. 4 quick calls. A shopping cart. It has to accept writes even mid-failure, and a brief disagreement is survivable. Bottom rung, tuned for availability. A user profile. Balanced quorum, 2 and 2 out of 3. Fresh enough for humans, and still up when a machine dies. Analytics counters. On a dashboard, a few seconds of staleness is invisible, so eventual isn't a compromise there. It's a feature. And locks, account balances, configuration that machines act on. Top rung, strong reads through a leader, because a stale answer there does real damage. Same ladder every time. You just ask what one stale read would actually cost, and buy exactly that much consistency. So here's the whole idea, one last time. Replication is copies. Quorums are the arithmetic of trust between those copies. Write to enough of them and read from enough of them that the 2 groups always overlap. Write plus read greater than the number of copies. And stamp every write with a version so the overlap can speak. From that one line of counting, you get stores that survive dead machines, serve honest reads, and quietly heal themselves as they run. Enough copies that the sets always touch. That's the lesson. Want to keep learning? Come find us at academy.rudewrite.com.